So basically what I would attempt to explain to you is all the terms related to radioactive decay using very simple understanding of how oranges or how you can calculate rotten oranges. So I will explain something as complicated as radioactive decay using the examples of rotten oranges. Okay, so how complicated are we talking about? We have definitions that you need to remember, which is decay constant. Taking note that this is probability of decay. All right. And we have the formula as well. And we have the next one, which is the activity. Also something you need to remember, rate of nuclear disintegration. Okay, but these are all very complicated terms and it's not easy to remember. But if we were to relate this to something as simple as rotten oranges, it's much easier for you to understand and remember. Okay, so let's go with that. What I'm teaching you is the approach is intuitive. So let's put it down. The approach I'm talking about is intuitive learning, which is you use something that you know to learn something that you don't know. So that's intuitive learning. Something that you know to learn something that you don't know. Okay? So let's start. Now imagine if you have 50 oranges in a box. So let's draw a box here. You've got 50 oranges inside. Okay, so visualize 50 oranges in a box. If I tell you there's a 0.2 probability. So probability is something you learn in secondary school, right? EMath. So that's something that you know. All right. If there's a 0.2 probability that some of the oranges inside are rotten. So usually we use the math language like this. P rotten will be 0.2. How many oranges do you think will be rotten inside this box? What would be the answer then? So you take so the actual number of rotten oranges would then be 0.2 times 50. And that's how you got 10. So this is what you know, right? Okay. Now this is the things you learn here. Decay constant and activity are the same thing. Okay. Let's say today, day one. The time frame is day one. Probability is 0.2. Okay, which means that there is a chance that I can find a lot of oranges, and the actual number is 10. Today I can find 10 rotten oranges. So how does this relate to decay constant? So decay constant, right, is like the 0.2 that I tell you about. The time is per second. I use per day. It's very similar. So per day is like per second. And that is called the rate. If you base something within a time frame, it's called the rate. So if you base the rotten oranges in a day, the rate is per day. If you base probability of decay in a second, the rate is per second. So you have the decay constant here, which is 0.2, similar to what we talk about here. Now, if I ask you, I say, Bumin, if I have, let's use this lah. If I have 50,000 nuclides, and the nuclides are similar to the oranges, that's why I'm using the same number, 50 and 50,000. Okay? And I tell you the probability of decay, the per unit time, per second is 0.2. How many nuclides are decaying in 1 second? Decay nuclides in 1 second. What would that be in terms of the math?
2,000.
Yeah, it'd be 0.2 times 50,000. Oh, 50,000 is there. Wait, let me just. 10,000. So what you get this number here, for per second, you have 10,000 nuclides decaying. That actually is the activity. So the point I'm trying to say is, let me just shift my head down here. The point I'm trying to say is activity is no different than finding out the actual number of rotten oranges that's happening in a day. Yeah. So what you're doing here is very, very similar to what you're doing for finding rotten oranges. And while the explanations are complicated, I hope you can appreciate that it is easier to understand if you're comparing to finding rotten oranges. Okay, and that is an example of intuitive learning, where you use something as simple as oranges, something that you know every day, to learn something complicated. Okay, and that's how you derive this formula. See, A equals to lambda n. This is a 0.2, and this is a 50. Okay, and this is something you need to remember. This formula is very important.